Today we are going to discuss the harmonic oscillator problem. Last semester we discussed the same problem but with an analytic technique. But this time we are actually going to use another technique called the operator method to solve the same harmonic oscillator problem. So we will use the operator method. So I hope all of you know the Hamiltonian of the harmonic oscillator, which we have seen in the previous semester. So the Hamiltonian of the harmonic oscillator is given by p square by 2m plus half m omega square x square. So the first term is the kinetic energy and the second term is the potential energy of the harmonic oscillator, and the sum of these two operators are the Hamiltonian, and in general this is the Hamiltonian operator for the harmonic oscillator. Now in order to find out the eigenvalues and eigenstates of this Hamiltonian, as I mentioned, here we follow a different technique called an operator method or a ladder method, which deals with operating algebra involving operators known as creation and annihilation operators. And this form a matrix formulation since various quantities here are expressed in terms of matrices. So let's introduce two dimensionless operators. So this p and x are taken as capital letters here in the expression for the Hamiltonian. Now we are going to introduce another two operators, a small p, which is connected to the momentum capital P by this relation capital P divided by square root of m h cross omega and another variable or operator small q, which is related to the position operator capital X into m omega by h cross, and these two are dimensionless quantities or dimensionless operators. In fact, these are called the field quadratures in quantum optics. Field quadratures in quantum optics. Anyway, we are not discussing about quantum optics or field quadratures, but these are the same things that you are actually going to define in quantum optics also. Okay, so with this introduction, we can write the Hamiltonian as h equal to, if I write capital P in terms of small p, I can write this as a small p square divided by 2m and then m h cross omega plus half m omega square, and if I write capital X in terms of a small q operator, this will be small q square h cross by m omega. So you can see that Hamiltonian is basically h cross omega divided by 2 into small p square plus q square. Okay, so let's put some numbers. So this is our equation number 1, these are equation number 2, and this is 3. And now we are going to introduce another operator. Let's say an operator A, which is defined as 1 by root 2 q plus ip, and a dagger, which is basically the dagger of a operator. So this is given by 1 by root 2 q minus ip. So we have introduced two more operators, a and a dagger, in terms of the dimensionless operators small q and small p. Okay, so you can see that both these are non-Hermitian operators. These are non-Hermitian operators because A and A dagger are different here. Now with this definition, let's see what is A dagger A. So A dagger A is basically 1 by root 2 Q minus IP into Q plus IP 1 by root 2. So this is 1 by 2. If you expand it, what you get is 1 by 2 Q square plus P square plus I by 2. What you get is QP minus PQ. So this can be written as half Q square plus P square plus I by 2 commutation QP, because QP minus PQ is commutation QP. So let's put equation number 5. Now in the equation number 5 we have seen that there is a commutation bracket between Q and P. So let's see what is this commutation relation. So let's calculate this commutation QP. So this is basically the commutation between square root of m omega by h cross x and capital P divided by square root of m omega h cross. So you have to calculate the commutation between these two things. So if you do that, what you get is, this is basically 1 by h cross. So what is it? Multiply these two things minus AB minus BA form. You have to do that. So this will give you 1 by h cross commutation XP. Right. Now commutation XP, we know that that will always give you IH cross. We have seen in previous classes. So this is basically I. Okay. So that means the A dagger A in equation 5 becomes A dagger A equal to half of Q square plus P square, small q and small p, plus I by 2 into I. Right. So this will be half of Q square plus P square minus half, because I into I will give you minus half, or you can write half of Q square plus P square is equal to A dagger A plus half. So if you substitute this in our equation number 3, what was equation number 3? This one, h cross Hamiltonian equal to h cross omega by 2 into small p square plus q square. So if you substitute in our equation number 3, what we get is the Hamiltonian operator is given by h cross omega into A dagger A plus half. So in equation number we have seen that the Hamiltonian is given by h cross omega divided by 2 into p square plus q square. So if you substitute for this half of p square plus q square in equation 3, what we get is the Hamiltonian becomes h cross omega into a dagger a plus half. Okay, so now we are going to introduce another operator which is called the number operator. Capital N, which is basically a dagger a, these product. So we are going to define this a dagger a, the product of these two operators, as another operator called the number operator, or sometimes it is called the occupation number operator. Sometimes it is called number operator or occupation number operator, and you can see that this is a Hermitian operator. Even though a and a dagger are not Hermitian operators, the product of these two are Hermitian operators. Now this is called number operator since it counts the number of energy quanta in unit of h cross omega associated with this system, so that we will see soon. Okay, so with this we can write the Hamiltonian as h cross omega, instead of a dagger a we put the number operator plus half. Okay, now you can see that Hamiltonian linearly depends this number operator n. That means if you take the commutation between this Hamiltonian and the number operator, so this will be basically the commutation between h cross omega n plus half and n. So you can prove that this will become 0. It's very simple. In 2 steps you can show that, 1 or 2 steps you can show that this Hamiltonian, they commutes, this number operator commutes with this Hamiltonian. So because of this, h and n have a complete common set of eigenstates. So those things we have seen in the previous semester, that the commuting operators have a common set of eigenstates. Thus the eigenvalues of capital N, we denote it by the small n. These are good quantum numbers for the harmonic oscillator, and we will use to label the common eigenstate. We will label the common eigenstate by this, the ket n. So this ket fulfills now, if you operate this number operator on this ket n, you will get some eigenvalue. That's what we have taken as small n times this ket. And what happens when Hamiltonian adds on these same kets? So you should get some eigenvalue times the same ket. Now we know that the Hamiltonian operator always gives the energy eigenvalue. So the eigenvalue that we get is the energy eigenvalue. So let's put this as our equation number. What was the previous equation? So we had equation 5. So let's put this is equation number 6. And let's say this is equation number 7. Now these states n are called the energy eigenstates. This is called the energy eigenstates, and En are the energy eigenvalues. Now the basis spanned by this energy eigenstates is called as the energy representation. So if you take this energy eigenstate as a basis, then this representation is called the energy representation. So we have already seen the momentum and the position representation. So since this is in the energy eigenstate, so this is called the energy representation. So we can now immediately write down an expression for the energy eigenvalues, because we have seen that the Hamiltonian is given by h cross omega into n plus half, right? So let's multiply with this energy eigenstate on both sides, so that will give us h n equal to h cross omega into n plus half, acting on the same eigenstates. Now on left side, what we get when Hamiltonian acts on this, we will get the energy corresponding to this eigenstate. So we put e suffix n, en, then n, and on right hand side what we have is h cross omega. Now when this operator n adds on this, what the eigenvalues we get is n. We represent these eigenvalues by small n. So this is n plus half times n, because we have seen that this is the eigenvalue relation for this number operator. So if you drop this ket n from both sides, you can see that the energy eigenvalue corresponds to h cross omega into n plus half. So this is the energy eigenvalues of the harmonic oscillator, where this n is a positive integer, which we will see soon. And this moment we don't have any idea what is the nature of this n, but we will see soon that this n will give you some positive integers. Okay, so this is the energy eigenvalue of harmonic oscillator. And now we have to derive a set of commutation relation between the various operators that we have introduced so far. So I will mention those commutation relations, and then you have to prove it yourself. So I'm not going to derive those things here, which will be an exercise for you. So the first commutation relation that we are going to derive is the commutation between A and A dagger, right? So if you remember the definition of A and A dagger, then this is half of Q plus IP minus Q minus IP. And this, if you do it properly, what you get is, this will be I in the commutation PQ. So commutation PQ means this is negative of commutation QP, so that will give you commutation QP is I. We have seen it just in the beginning of this class. So this will give us I into minus I, so that is equal to 1. So we have one commutation relation, A dagger is equal to 1. Okay. Let me put this as equation 8 and this as equation 9. So you have to do it as an exercise. So this is an exercise for you. Now the second commutation relation is the commutation between A and H. A and the Hamiltonian. So this is basically the commutation between A and the Hamiltonian. We have seen that this is h cross omega A dagger A plus half. So if you do that, what you get is, you will get h cross omega a. So this is equation number 10. So all these commutation relations are exercises which you have to do it yourself and submit to me. Now the third commutation relation that we are looking for is a dagger and h. So a dagger and h is also basically the commutation between a dagger, and then in place of h you have h cross omega into a dagger a plus half, which you have to prove as this will give you minus h cross omega a dagger. Okay. Now the fourth commutation relation is the commutation between n and h. So you have to prove that this is 0. We have just mentioned it to derive the eigenvalues of energy, but you have to prove that this is 0. Now let's again consider this operation, the Hamiltonian operator acting on this n kets. What you get on right hand side is the energy eigenvalue and like what we have seen just before, right? Now let's multiply both sides of this expression from left side by the operator a. That means, so if you multiply with the operator a from left side, what you get is a h n is equal to, n is some number, then you have a n, right? Now from this commutation relation from our equation number 10, we have seen that the commutation AH, or in other words, what you have is AH minus HA is equal to H cross omega A. So that means AH can be written as HA plus H cross omega A. So this equation can be written right now as A H n is equal to, in place of A H n, what you can write is H A plus H cross omega A, then this n. Then on right hand side what we have is En An, or can write H A n equal to, if you take these terms to the right hand side, what you get is En minus H cross omega An. So let's put equation number 13 here. Now you can see that if n is an eigenvector of H with an eigenvalue En, then An is also an eigenvector of this operator H, corresponding to an eigenvalue lowered by H cross omega, right? So the eigenvalue is lowered from En by 1 unit of H cross omega. Similarly, we can prove that H a dagger n is equal to En plus H cross omega a dagger n. So the same way like what we did for this equation 13, we can prove that this same kind of a relation for the a dagger operator. If you do it, then you get H a dagger n is given by En plus H cross omega a dagger n. So what does that mean? It tells you that a dagger n is also an eigenstate of this Hamiltonian h with an eigenvalue given by En plus h cross omega. So now you can see that the respective actions of A and A dagger on N is to generate new eigenstates that are lower and higher by 1 unit of h cross omega. That means if you use A, then the eigenvalue is lowered by 1 unit of h cross omega from its En, and if we use A dagger, so this is eigenvalue is raised by 1 unit of h cross omega. So A and A dagger acting on this state n either lowers the eigenvalue or raises the eigenvalue by 1 unit. So as a result, these A and A dagger are respectively known as the lowering or and the raising operator. So this A is called the lowering operator because you can see that the action of A on n is to lower the eigenvalue by 1 unit of h cross omega, and A dagger is called the raising operator. The raising operator because the action of A dagger on n is to raise the eigenvalue by 1 unit. Now this is also known as the annihilation and creation operator. So this lowering operator is also known as annihilation operator. Annihilation operator, and this is also known as creation operator. Okay. So next let's determine the eigenvalues n of the number operator. So we have seen just that the capital N acting on these eigenkets n will give you some small numbers n, but we don't have what these small numbers are exactly. So let's see how to get an idea about this number. So for this we consider the commutation relations of n and A. That is commutation n A. So this is basically A dagger A and A, the commutation between A dagger A and A. You can show that this is simply commutation between A dagger A plus A dagger commutation A. Now you can see that this is equal to 0, and A dagger A we have derived previously. So this is given by A dagger A is given by -1, right? So you can see that this is simply minus A. The commutation between n and A is simply minus A. So this is equation 15. Similarly, you can show that the commutation between n and A dagger is equal to A dagger itself. Let's say equation number 16. So what we have seen that A and A dagger do not commute with this number operator. So that means the eigenstates n or the eigenkets n of the capital N operator are not the eigenstates of A or A dagger. N are, so they are not the eigenstates of A and A dagger because they are not commuting operators. However, we see what is the effect of this commutation NA acting on this kets n, small kets n. So this is basically NA acting on n minus AN acting on n, right? So this can be written as n AN minus A, and these are the eigenstates. So small n are the eigenstates of capital N that will give us the eigenvalue small n, right? So this can be written like this. So this is capital N minus a n, right? But we have just seen that from equation 15 the commutation na was minus a. So this was our equation number 15, right? So on left hand side what we have is basically minus a into n, or you can write minus a n plus n a n, that is equal to, on right hand side what you have is capital N a n, or you can write this n a n is equal to, this will be n minus 1 a n. So this is our equation number 17. Now you can see that the effect of a acting on this n is that it lowers the eigenstates n by 1 unit, right? It lowers the eigenstate by 1 unit. So it's something like what you can infer from this expression is the effect of a acting on n is to generate an eigenstate which is lowered by 1 unit. It's not an eigenvalue, it is to generate an eigenstate lowered by 1 unit. Why it is? Because if this is the case, then you can see that if you add this number operator on this state, you can see that you will get the eigenvalue of that operator, then n minus 1, because these eigenkets n are the eigenkets of this number operator, so that will give you a corresponding eigenvalue then the same operator. So this is exactly what we have here in equation 17, n minus 1 into then an. So if you consider the effect of an is like generating a state n minus 1, then these two things are same, these two things will be same. So what we infer from this equation is that a, whenever it acts on this small n eigenkets, that will generate a new state which is lowered by 1 unit. So if it acts on n, that will give you a new state n minus 1. So that means this a n and this n minus 1 eigenstate are same up to some multiplicative constants. So you can write a n as something equal to some constant cn into n minus 1. So let's put some number. This is equation 18. And in a similar fashion, what you can show is that similar to equation 17, you can show that this n, a dagger n, equal to, what you get is, on right hand side you will get n plus 1 instead of n minus 1, since these are raising operators. N plus 1 a dagger n. Now with a similar argument which we have put for this equation 17, you can prove that the effect of a dagger acting on n is something like so this is basically what it does is it creates a new state, because you are getting an eigenvalue n plus 1. So what you have here is a new state n plus 1 with some eigenvalues. So these are connected by some constants. Let's say this time some constant dn. Okay, so this is our equation number 20. Now we are going to deal with these two equations, equation 18 and 20. And from 18 we have seen that a acting on n will give you cn into n minus 1, and Cn is a constant, so which can be determined from the requirement that the state n is to be normalized for all values of n. So what we do is we are trying to normalize our equation number 18. So when you do that, what you have to do, you have to take the complex conjugate of that, so that will be the respective bra form. So this will give n, then the complex conjugate of a will give you a dagger, okay, multiplied by a n, on right hand side modulus Cn square, because Cn into Cn star, the complex conjugate will give you modulus Cn square, then n minus 1, n minus 1. Because the complex conjugate of n minus 1, the ket n minus 1 is given by the bra n minus 1. So that is how you get these bras here. Okay. If I remove these brackets here, you can see that this is n a dagger a n is equal to modulus Cn square n minus 1 n minus 1. Now a dagger a is the operator capital N, right? So this is same as right hand side. Now n acting on n will give us, this will give us an eigenvalue small n times the eigenstates. So what we have as a result of this operation is eigenvalue n, then ket n, and on right hand side what we have is Cn square n minus 1 n minus 1. Now since n is a normalized state, this will give us 1, and if n is normalized, n minus 1 will also be a normalized state, so this will also give you 1. So what it gives you is that modulus Cn square is equal to n, right? This modulus Cn square will always be a positive number. This will always be a positive number because it's modulus square of something, which will always give you some positive number or 0. So it implies that the right hand side should also be 0, or it should also be always a positive number. So we get an important clue about this number n here. It tells you that this n must be greater than or equal to 0 because of this condition, because Cn square can never be negative, it's a modulus square quantity. So whatever be these quantities small n, it must be some numbers which is greater than or equal to 0. It can never be a negative number, since norm is a positive quantity. Okay, so that means you can write this expression an. We have seen that from our equation 18. We have seen that this is an is given by some constant into n minus 1, right? Now that constant, we have seen that it is given by square root of n from that expression. So this can be written as square root of n into n minus 1. So that is our equation number 21. This means that the repeated application of operator a on these states n, it generates a sequence of eigenvectors n minus 1, n minus 2, n minus 3, etc. Because each action of a will lower the eigenstate by 1 unit. So repeated action will generate basically states like n minus 1, n minus 2, n minus 3, etc. Okay. So since we have seen that this n can never be negative, or n is always greater than or equal to 0, there must exist an eigenstate with an eigenvalue n minimum such that when we apply this operator A, we no longer step down the eigenvalue, but instead we hit the lowest possible eigenstates. So you can write when this A acting on n minimum, then you should get 0. It should not take you to an eigenstate lower than n minimum, because of this condition, n must be greater than or equal to 0. So these sequences has to terminate at 0. So this is an important result for us. Let's say this is equation number 22. So there is a minimum eigenstate below which you can never go by the action of this lowering operator. Okay, because why is it like that? Because A, by the nature of A, what we have seen is that we should go to a state in minimum minus 1, right? But there is no such state exists. That's our argument. There is the minimum state is the n minimum. So this should not be true. Okay. Now in a similar fashion, we can show that the action of a dagger on n is, we have seen that this is given by some constant dn into, and its effect is to raise the eigenstate by 1 unit, and you can prove that similar to the way that we have shown that this n square is equal to n. You can prove that this dn is basically given by square root of n plus 1. So what you have is n plus 1 into n plus 1. Okay. So what we have seen is when A acting on n will give you square root of n into n minus 1, but when A dagger acting on n will give you square root of n plus 1 into n plus 1 state. So this is equation number 23. So this equation again implies that the repeated application of A dagger on n should generate an infinite sequence of eigenvectors. So it should generate states like n plus 1, n plus 2, n plus 3, etc. Okay. So since this n is a positive integer, the energy spectrum of harmonic oscillator is discrete. So we have seen previously that the energy eigenvalue is given by n plus half h cross omega, and we did not say anything about n there, and now we have obtained some clear idea what this n is. We have seen that this n can be either 0 or positive integer numbers. Okay, so it tells you that the eigenspectrum of harmonic oscillator are in fact discrete. So if you plot the energy eigenvalues, those are equally spaced energy levels. So for n is equal to 0, what you get is half h cross omega. For n is equal to 1, we get 3 by 2 h cross omega, 5 by 2 h cross omega, 7 by 2 h cross omega, like that. So those are equally spaced quantized energy states. Now the ground state energy is obtained for the lowest value of n, so that is n is equal to 0, and this is given by, this lowest value is given by half h cross omega, and you can see that it's a non-zero energy, and it is called the 0 point energy. It is the 0 point energy, and it's a non-zero quantity, and I had told you in the previous semester what is the implication of this thing. It's basically a direct consequence of Heisenberg's uncertainty principle. And now let's go to the some more implications of these operators. So let's consider this a dagger acting on n. So this is given by square root of n plus 1, and then it generates a new state n plus 1, right? So that means we can write this n plus 1 as 1 by square root of n plus 1 a dagger n, right? So if you put n equal to 0, the first state that we can generate from it is given by 1. This is given by 1 by square root of 1, which will give you 1 itself. So this will be a dagger acting on the 0th state if you take n is equal to 0. Now if you take n is equal to 2, or if you act this by one more thing of a dagger, then you can write this 2 is given by what you have to get the state 2 according to this expression. To get the state 2, what you have to do is, this is given by 1 by square root of 1 plus 1, then a dagger acting on the state 1, right? You will get this for n is equal to 1 state. So this is basically 1 by root 2. And what is a dagger acting on 1? That we have already seen here. A dagger acting on 1 will give us the same as a dagger acting on 0. So this is will be written as a dagger square acting on the 0th state, right? Or if I want to generate the state 3, what I have to do is, according to that expression, this is given by 1 by root 3 a dagger acting on 2. Now you can see that this is given by 1 by root 3, then a dagger on 2 is given by this expression. That will give me 1 by root 2. So I will get one more a dagger, 1 by root 2, a dagger cube acting on 0. So this is same as 1 by root 3 factorial a dagger cube acting on 0. If you generalize this, you can show that any state n is given by 1 by square root of n factorial a dagger raised to n acting on the 0th state. So what it tells you is that to find any excited eigenstate n, we need simply to operate a dagger on the ground state for n successive times. So if you operate this a dagger n successive times on this ground state 0, we will get the respective excited state. Okay. Now any ket n and n prime corresponding to different eigenvalues must be orthogonal, because it's a property of the eigenvalue equation or with the Hermitian operators. So you can say that the inner product between n prime and n is equal to delta n prime n. So we have seen that all these states like 0, 1, 2, because n is basically some numbers, etc., are the simultaneous eigenstates of the Hamiltonian and the number operator n. So we can say that this n, the set of n, it constitutes an orthonormal and complete set of bases. And complete orthonormal set of bases. That means you can write, so complete orthonormal set of bases means we have already seen that the inner product between n prime and n is equal to delta n prime n, and the completeness condition tells you that if you count over all these possible um, states and the projection operators of these states, this must be 1. Okay,